also going to be doing a field hike for us in the afternoon, and then we're going to go to, after Larry, Dr. Jacqueline Cortell is going to talk to us about first geology and then all the habitats that arise from that is what so we're going to have 2 lecture speakers right now, first Larry, then Jacqueline, and then out in the field. Good? All right, yes, you're welcome. Thank you all.
So I'm Larry Bean. I work for the state, the Department of Environment, Great Lakes and Energy. Started out with DNR, then it was DEQ, multiple, changes in departments. But basically doing the same thing, dealing with landfills and hazardous waste. I worked as a geologist for the state for 21 years, and now I've been working as a supervisor, supervising the Jackson District Office and the Lansing District Office for 13 years. So this is a little bit challenging for me. I'm dealing with some bone cancer issues, and the doctors have taken out lots of parts, so this leg isn't very well connected here. So when we go to the quarry, this is really hard because normally I'd be all over that quarry and climbing all over everything. And so, but I can barely get around now, so I'll be out there with a little motorized cart and that they provided, and I have a walker. I can get around a little bit, but I'll do the best I can if you can have some patience. So, but let's start with glacial geology in Michigan, how the Great Lakes formed, and the deposits we have here that we have to work with to understand our ecosystems around us. So let me start with that. Any questions on this so far?
You might see the slides better if you didn't have the light on, I don't know.
So let's go back about 2.5 billion years when the continents were starting to form. You had different pieces of continents floating on the mantle, on the globe, and moving around. We still have plate tectonics and plates moving around. And some of those smaller continents were coming together to form the North American continent that we have now. And that was occurring 2.5 billion years ago. So we had plate tectonics. My pointer doesn't work on the screen, so we use that. So we have subduction zones, and the continents are floating on the mantle. The oceanic crust, the basalt floats on the mantle. The oceanic crust, oceanic crust is a dense basalt, so it floats lower on the mantle, like an oak board floating low on water, compared to the continent, kind of like styrofoam floating higher on water. So the continents float a little bit higher on the mantle, the lower rocks, the material below, and the ocean crust sits lower, and that's why the ocean water then finds the low areas, and that's where it sits, because that's lower on the globe, all the way around the globe. And that will play an important part of glacial geology. And so here we have, I have a pointer, but it doesn't work on this screen very well. But this, can you see this pointer all right?
Yeah.
Okay. So we have what's called the Canadian Shield, and so some of those rocks that were coming together 2.5 billion years ago are still up in Canada, north of us. And some of the rocks we see in the quarry here today came from there. So if you see igneous or metamorphic rocks, that Reading Rocks brochure goes over some of this, and it points out how these rocks are 2.5 billion years old up here. And so if you see igneous or metamorphic rocks down here, the glaciers brought them from this area here down to this part of Michigan here. And you know, if the igneous and metamorphic rocks, they're about 1 to 2 billion years old, in that range, typically. Now, about 1.1 billion years ago, the continent started to split apart. It started to rift, kind of like East Africa now is starting to break apart. And if it continued, then you would have had a new continent over there, a different continent here, and a new ocean in between, and new oceanic crust in between with a new ocean forming, but it failed. But for a while you had basalt coming to the surface, the very dense type rock, coming up with volcanoes. So we had volcanoes in this part of Michigan. And it was that really heavy rock was being dumped on top of the continent, so now it's an unstable situation. You have that light continent floating on the mantle, but now you have a really heavy, dense rock dumped on top of that. So what happens then? So up in the Upper Peninsula area, you had sagging and you had faulting, and that ultimately led to the formation of Lake Superior, and the glaciers helped to carve that out. But we're going to concentrate a little bit more on the lower part of Michigan. In the lower part of Michigan, the very dense rocks started to sink back down to a lower level because they're very heavy. So they started to sink back into the mantle, and pushing the crust down is a big basin. It was like a bowl. And then sediments washed in and deposited. So sand washed in and eventually became sandstone. Clay washed in, eventually lithified into shale. You had carbonates being formed. You had coral reefs here. And part of this time, this part of the continent was actually south of the equator, and then passed through the equator and came up to here. So when a lot of these rocks were forming here, it was very warm and tropical environment. And so we had coral reefs being deposited in this basin. And so as it sank, more sediments came in. And so when you think of sedimentary rocks, you just typically think of layer cake. You know, you have sand and it becomes sandstone, and clay becomes shale and limestone. And you know, and they're kind of layers of a cake. But in this case, they're forming in a big bowl. So it's more like soup bowls stacked on top of each other. And then the oldest rocks are on the outside, the first bowl, and it goes way down underneath. In the center of Michigan, more than 10,000 feet down. And then the newest rocks that formed were up in here, around the Pennsylvania time, 300 million years ago in there. So this was occurring between 900 million years and 200 million years, that this was sagging back down and the sediments were washing. This was an inland sea that was continually sinking and continually gathering more material that became sedimentary rocks in this bowl fashion.
Okay, I'm gonna interrupt just for a minute. I'm his lovely wife and assistant here, but I'm just gonna help him with this call. So Larry belittles what happened to him. He lost his right pelvis completely. They took out his entire pelvis because of cancer. And he also had a stroke after his surgery, because it was 11 hours long. And so he can't see over here. So I'm gonna hold the pole for you, okay?
Okay.
So you don't have to, he's trying to search over here and he can't see. His peripheral vision is gone, so I'm just gonna hold it for you, okay?
Okay.
There.
So these rocks were building up, and here it just shows the time frame. And it was probably full into about here, but then the basin, the Appalachian Mountains formed, and that was a little bit more push on the continent, so it caused a little more sagging, and then it was a little bit more filling, around 270 million years ago in that time frame, because of that, and then it was down. So this is what it looks like. I'm looking at two different screens here. Okay, yeah, so this is a map of these bedrock, these deposits that are in a bowl shape and outcropping in a circle. Now, looking at a cross section, this black rock here, this black deposit, is the speckled, actually the speckled part right here, the dark speckled, is the Niagara Escarpment. So it's the dolomite that forms Niagara Falls over here. It forms Bruce Peninsula over here, the southern part of the UP, Green Bay over there, and the peninsula is over there. It's a very hard, resistant rock. It's also underneath Chicago and down over here. So that played a part in helping to guide the glacier movement through this area. When you look at where that's right here, that speckled rock right in there. on top of that were evaporates. So there's a period of time when the ocean, or the inland sea, was very saline, and you had salt and gypsum deposits forming. So going 1,100 feet below Detroit, you have 30-foot thick salt layers that were forming. It was a very saline, like the Dead Sea environment in here. Now, but then after 200 million years, after this was all filled, then groundwater started to flow through here. It started to dissolve that. So salt and gypsum is what you use to make drywall, and it dissolves in water. And so when groundwater came through, it dissolved it, and then the rocks above that, up here, collapsed into that. And so when glaciers come through, whenever there's a weak zone, where rocks are rubbleized, the glaciers tend to just sweep that away. And the glaciers are very aggressive at taking away debris. And that's what happened here. Because of that collapse into the zone that was washed out, the rubble was left, and the glaciers came through and took care of that. And so here's the black Niagara Escarpment was really influential in helping to guide the glaciers through. Now, before the glaciation, this is what we believe the drainage looked like. So drainage patterns set up, taking advantage of low areas and going around the resistant rocks like the Niagara Escarpment. And so we believe that this is, how the rivers were set up at that time, before glaciation. And then we had the glaciers advanced and retreated multiple times. There were 4 main advances, and there were other sub-retreats, and as you could count 11 advances if you want to get into all the sub-stages. And so every time the glaciers came south, they carved the rocks below, and they picked up debris, and they carried that debris with the glaciers and moved that debris south. And when the glaciers retreated, the glaciers didn't go backwards. Actually, the glaciers are still flowing forward, flowing to the south, but melting faster than they were moving forward. And bringing debris like a conveyor belt to the end that was melting, and dumping that debris off the end of the glacier that was melting, and was still flowing forward in the conveyor belt, and dumping all that debris off the end as the end of the glacier, the top of the glacier melted away.
How long ago was it?
So the glaciers occurred between 2 million and 10,000 years ago. There were multiple advances and retreats within that time frame, 2 million to 10,000 years ago. So you can look at, when the glaciers stopped for a period of time in one spot, they dumped debris into that spot. So they're moving forward, they're dumping the debris off the end of the glacier, because the glacier is melting and debris just piles up. And so it forms what we call a moraine, an end moraine. So it's a big ridge of debris. And so there are 4 good lines of debris, moraines, set up here for those 4 major advances. There's the Nebraskan, the Kansan, the Illinois, and the Wisconsinian advances, where we can see good endpoints for those. And they came down to about the Ohio River at times, all the way through Ohio. And in this part of the globe, they extended further south than other parts of the globe, I think because of the Great Lakes basins, where they were deeper, the ice was deeper, the ice flowed readily through there, it was wet, and moved readily through there, and so it was able to come further south, get pushed further south in this part of the globe than other places around the globe. And this is what it would have looked like. I mean, this is Greenland, but it would have looked like this, a big continental ice sheet. Now here's a glacier that Kathy and I looked at. So we'll look at this a little bit. So you can see the glacier there, it's melting. You can see some of the debris piling up here. This is up in the Canadian Rockies, between Banff and Jasper. And here you can see the glacier coming off the top of the mountains there. This is more of an alpine situation, coming down here and melting here, creating an end moraine there. There's lateral material that's carving the edge of the mountain there, and bringing debris down here. This is a lateral moraine and then moraine down here. And you can see some ridges down here, and then there's water coming off and creating deposits down there. We'll talk about that. So here's some water running across the glacier and going down into cracks and creating shafts and dumping down to the lower part of the glacier where it then flowed. And it's picking up sand and gravel and moving the sand and gravel with it. So like a regular stream, like say the Huron River, it moves sand and gravel and deposits sand and gravel. And anything that's too big for it to move gets left behind as part of its deposit. Any of the fine grain material, the clay and silt, fine sand, it will carry further downstream until the water level slows down and the energy slows down, and then it drops out of suspension. Now this is underneath the glacier. That's Kathy there. And you can see there's the water's flowing underneath here. There's sand and gravel down below that's being deposited. There are big boulders here. Now the water flow isn't great enough to move boulders that size, so those boulders were in the ice up there. And when at times in the summer, this is in September, in the summer this whole cave is full of water and it's carving, melting the ice upward, and those boulders were in the ice and they just dropped out of the ice and just fell, and that's where they lay. And then now the stream is running along underneath there and depositing sand and gravel around those boulders. We'll see if the pit we're going into is kind of like this. Sand and gravel, and we got big boulders to look at.
There's a question in the back.
Go ahead.
Yeah, if you don't mind. I've always been unclear about the movement of the glaciers and what causes it. I mean, in this case, you've got a downhill situation, so gravity is presumably dragging that ice downhill.
Yeah.
But when you start talking about North America or
Yeah,
the Midwest,
the whole continental ice sheet, yeah.
what is I mean, there's no, the gravitational force doesn't go from north to south, so how is
No,
it that those
but it is gravity, and it's the conditions of ice. So if I saw an example where, it was in a video, where a tube of ice, a pipe, had ice water frozen in it, and then they put a hydraulic press on it, and pressed down on it, and there was a hole in the side of the pipe. And they just pressed down, and the ice began to flow and squirt out like toothpaste out of the little hole in the side of the pipe. Just from that pressure pushing down. So it's like that. So as the weight of the ice, when the ice gets about 1,000 feet thick, the bottom part turns into little beads of ice and starts to flow as a mass.
Yeah, okay.
Under the pressure, the weight of the ice on top of
So it's
it.
kind of
And so it begins to
pancaking out.
flow, and it will flow downhill. In this case, from the north to the south, and it goes downhill or away from the area of accumulation. In this case, things are pretty flat.
Right.
So it accumulated up in Canada to the north and east of here was the major accumulation. And during the major advance, when the ice went all the way down to the Ohio River, it was about 2 miles thick up in Canada. And here in this part of Michigan, it would have been about a mile thick, according to calculations that people who study the flow of ice. And in order to push it all the way down to the Ohio River, it would have had to have been 2 miles thick up there and about a mile thick here.
So that flow then is kind of a flattening out of this ice mass, and it just pushes out.
Yeah, it
all
just
that?
pushes it out from underneath.
Thank
Yeah, and water helps to move it. I have a slide that comes up that I can kind of show some of that, how it moves in different ways. But that's basically how it occurs.
That's a really good question.
And the accumulation area is an area of the greatest accumulation of snow and least melting. And so the glacier ice is really just snow that piles up and eventually gets compacted and turns into glacial ice. And it's just over thousands of years. This isn't a short time frame. This is thousands of years that it accumulates and flows like this. Yep. Where?
Oh, sorry. so like at the same time period that it's going across Michigan and, you know, ending in Ohio River Valley, is Michigan at that time like that sea with the coral in the bowl, or does it
No,
already have land
No,
mass?
see,
already
that
there?
was from 900 million years ago to 200 million years
Alright,
ago.
so this is after that.
And then from 200 million years ago to 2 million years ago, you had erosion in those river valleys that formed. And the water flowing off to the east.
Yeah, but the Great Lakes were the ones that helped kind of push it farther in those pockets.
Yeah,
you're
but
saying.
because you had those valleys that were created by the running water,
Right.
then the glaciers took advantage of those and carved those out and made those big U-shaped glacial valley. And then the ice was then thicker then. And the thicker it got, the thicker the ice got, the deeper the Michigan basins, Michigan lake basins got, the faster it flowed.
And the second part of my question is the opposite of that, like the driftless region in Wisconsin,
Yeah.
Is it just hills that prevented it, or is it heat and conditions that prevented that from getting scraped off?
There's some resistant rock there.
Okay,
The ice stalled out. It went preferentially around that and then down the Lake Michigan basin and over to the west of there. And I think in there and in the center of Michigan, for a long period of time, the ice was frozen to the ground and wasn't eroding the ground. And it went flowing around preferentially through the
so it just
basins,
had a
but
spot where-
frozen in the middle. And there's a slide I have that kind of demonstrates how that works. And then the ice moves above by shearing and moving above, but frozen down below and still flowing above and flowing around through the basins. And so it doesn't cause much erosion. And there's not as much, the driftless area means drift is the debris left by the glaciers. That's just all the soil and rocks and things. The general term for that is drift. And in that area, there's not much of that because the glaciers didn't flow through, didn't carry much debris in there. They went around. There was a little bit of debris in there, and then the ice melted away. It was frozen to the ground and it melted away, and there just wasn't much debris left to deposit. So there's just not much there. Now, this one shows, this is that same Athabasca Glacier, the glacier here, and some of the moraine material. So you can see a lot of different types of deposits in close proximity here. And when, for your class, you know, you want to talk about the plants that would grow in this environment. So these moraines have mostly clay. There's a lot of clay in it, and rocks of all different sizes. So a lot of the moraines, if you dig into them around here, you know, try and dig in them, they're kind of hard and pretty dense clay. And that's what you would have there. And the plants that were growing there would have to, you know, the roots would have to penetrate through that clay and around those rocks in order to grow. But then right next to that, you have flowing water coming over here, and that flowing water is carrying sand and gravel, and so you have deltas of sand and gravel occurring over in here and around here. So you can see the stream coming off the glacier and out from underneath the glacier. This is actually coming out from underneath the glacier here and flowing over here. And so it's depositing these deltas of sand and gravel. And so you have those right next to the areas with dense clay. And then out over here, you have rock flour. When the glaciers gouge and grind and erode the rock, they grind it into a rock flour. So you have, it looks kind of a funny paley blue here because there's that rock flour floating in suspension that is clay size. So you have clay minerals. Clay minerals are a sheet silicate, and most of what you have here is clay sized particles, this rock flour. Now the sheet silicate clay, that absorbs water when it's in, say, a soil, and it absorbs water in the structure. It's just the way it works with these little sheet silicates in it, and the water is absorbed right into the structure of the mineral. Here it's just this powder, like flour, just real thin flour, and then the water does, it gets stuck in there, but it's not really getting into the structure of the mineral, really. Now there is some clay mineral here. If the glacier eroded some shale, then there would be some clay mineral mixed in. And we do have that here because, say, around here in the Lake Huron Basin, there is some shale there that the glaciers gouged away and brought out and then broke up. And that broke up back into the clay particles because it's soft and crunchy. And those are clay minerals, so the shale is actually the clay minerals. And that's the sheet silicate. So there is some sheet silicate mixed in here, and that would help absorb water in the structure of that. So this shows that there's a lot of varying environments, different botanical type environments that would occur in close proximity here. And it's the same where we are here around this part of Michigan. So this is just a good example, a lot of stuff in close proximity. Now here's, some examples of eroding the rock. So this is Kelly's Island on Lake Erie, and it just eroded that rock. And it's not like a big boulder, I was taught in school, oh yeah, like a big boulder just gouged through there, carved it like butter. It doesn't work that way, not at all. So it works like this, so you can see ice moving over here, and it's making these big grooves in this rock, and the grooves are forming, they're from the erosion, sand and gravel within the rock, or within the ice here, is carving into this layered rock, the sandstone, maybe limestone, this layered sedimentary rock, but it's taking advantage of some of the soft layers and eroding some of the soft layers and leaving some of the hard layers. And so it's forming those big grooves like you have on Kelly's Island. So this is a good example of how that occurs right there. And then we can look at some of the details of hard resistant things within the rock and how the ice flowed around, so we can tell which direction the ice was flowing. If you have a groove, if you have a scratch, you can say, well, the ice either went that way or it went this way. Not sure, but in general, like around here, you'd assume, okay, well, it came from the north, based on all the other evidence we have around here, it came generally from the north and went south. But we can make that determination better by some of these types of details in the rock. So here's a resistant pyrite mineral, and the glaciers formed and carved around that hard mineral there, and then flowed off this way. So you can see that the ice then flowed this way. It just, we can tell that by studying how the erosion of this material. Now, I'm seeing two different things here. Oh no, okay, I get it. Another picture, and I wanted that one. Okay. So this is, some plucking away. A big rock will gouge and pluck away at the lower rock and form these types of shapes the other way out. And then here's, I took some, a measurement of some striations, and there were some other grooves. This is up by north of Port Huron. And measuring the orientation of the things, and then there's in here, it's kind of faint, but you can kind of see a trail right in here that's narrow there and wider here, and that would have been from a boulder like this, gouging into the rock. As the glacier moved that rock along, it gouged, it rotated, and popped out some rock, moved it forward a little bit more, popped out a little bit more, but then the rock was breaking up at the same time and getting wider, and having bigger contact, and so it gets wider as it goes down. And so we can tell the ice went this way in this location. And so that's up here, the red arrow there shows that those measurements were taken up there, and so my compass showed that was the direction of the ice flow in that location. And then this is up in the Keweenaw Peninsula, and you can see some grooves in here in the rock, the basalt rock. And this is actually the basalt rock from that came up in those volcanoes over like about 1.1 billion years ago that caused the basins to form. This is some of that rock. And taking measurements, and you can see up there how the ice moved across the Keweenaw Peninsula there. Now you can see the black. This map shows the end moraines of the glaciers after the glaciers retreated away. And it shows that the glaciers retreated away in lobes, and the ends of those lobes are traced by these black moraines. So here's a big lobe, and there's a big lobe, There's another big lobe. But when the ice was moving and overriding the whole area and eroding the bedrock, you can see the direction. Some people thought that the ice was flowing this way in here and flowing this way through here. Well, it was when it was getting thinner, but when it was eroding the rock, it was different at times. So we're looking at two different things. So here's some striations down in Monroe County. So you can see the arrow down here, Monroe County. You know, some people thought that all the flow went across Lake Erie and went out this way to form these moraines. That was only when it was melting in the last breaths of the ice sheet, as it was melting away and splitting, getting thinner and splitting into different lobes and stopping for a period of time to dump material off the end of the lobe to make these curved end moraines. But when the ice was flowing, when it was thicker and flowing across the whole area and going down into Ohio, it was flowing this way, and up there going that way. So you can't go by just the end moraines on some of these. So here's the ice overriding the whole area, but then starting to split into different lobes as it was starting to melt, thin down, melt. And then also, another reason it went into lobes is because it was flowing preferentially through those Michigan basins that were created, that were carved out by the moving ice. And all that debris, that rubble that from the sedimentary rocks that collapsed down into the void that was left after these evaporates, the salt and gypsum dissolved away by groundwater, that rubble then was just picked up by the glacier and swept away, making those basins. And then the ice preferentially moved through there. Now here's a good model of the movement of ice. So in some cases, the ice is cold-based and frozen to the ground and not eroding the ground at all. Some places it's warm and melting and there's water and it's eroding and then dumping. In other areas it's dumping more material and it's eroding, and that's toward the end of the glacier over there. And here warm melting and eroding away. And then the ice over here that's eroding away and melting is then flowing over top of the ice that's frozen to the ground and shearing and flowing out over that way. So here's another model showing the ice moving. It's eroding the ice or the rocks down here, and then in some places it's depositing till the material that makes moraines. We call it a till. It's a lot of clay, but it also has silt, sand, and rocks of all different sizes mixed in. But it's jammed in under the weight of the ice, so it's very dense. When drillers are drilling and they're going through softer sediment above and they hit that till that has been pushed in underneath by the weight of the ice, they know it. The drill rig bogs down. You can hear the engine of the drill rig going slower. Any question?
I have a question. So the Great Lakes have already been formed at this point?
They weren't Great Lakes, they were basins that were being carved out and created.
So what you're talking about is also creating the Great Lakes basins?
Yes, so there are two different things. We got the sedimentary basin that formed 900 to 200 million years ago for the sedimentary rocks, as an inland sea, and now we're talking about the glaciers carving away and making these lake basins. So it's a different type of basin.
So there's different.
Yeah, we have, and this is, and so the glaciers occurred from 2 million to 10,000 years ago, and during that time they were carving out these valleys and taking advantage of the weaker rocks and making these big U-shaped valleys. Glaciers like to make U-shaped valleys, and those are the lakes that we have, the lake basins that we have. And you notice how Lake Michigan is a good example. Just a big, huge U-shaped valley. It's carved out by glaciation. Glaciers like to make those types of valleys. It's just a stable environment for them. So, but this shows how the ice is moving. It's picking up debris. It's melting at the end, and the debris coming off the end is the end moraine material, and it's kind of soft because it's just dumped off the end and just piled up in a pile. Now, it's on top of that lower till, so this is where, an example where you have, material that's not real dense, you know, and so like I was mentioning, a driller drilling, the drill rig would go through that moraine material pretty quick and then hit that lower, older till that was packed in under the weight of the ice, and that's gonna be really hard. And then as water, you have a huge ice sheet melting away, like you saw that picture of Greenland, that's what it looked like here. Huge ice sheet melting away, a lot of water. And so that water is carrying sand and gravel with it. And so there's this, you know, braided streams, deltas, and big deposits of sand and gravel that are forming out beyond the glacier. And we're gonna look at that. This is a good model for what we'll look at the gravel pit up the road, in a way. And when we're left, after the glacier retreats, we're left with a ridge where the end moraine was, right in here, where the glacier stopped for a period of time, still was flowing forward, but melting as fast as it was flowing forward, and piled up debris here for a period of time in one spot. Outwash plain, a lot of the sand and gravel that the water deposited out beyond the moraine, and till, you know, packed in underneath the weight of the glacier up there, and the glacier ran away. Here is going back. Here you have a water flowing underneath the ice and coming out, and there's a tunnel. There's an ice cave there, and kind of a lake deposit there. And when the ice melts away, what's left is an esker. So in those situations, the water flowing underneath the ice is depositing sand and gravel and then melting up into the ice. And the reason it goes up, you'd think with gravity that it would just go off to the side and melt laterally. But because of the weight of the ice is pushing down, and there's more pressure down below. So it overrides gravity. So that weight of that ice is pushing down here, forcing the water to melt up here and depositing the sand and gravel. So there's less pressure up. So it builds up, and it builds a ridge of sand and gravel. And we see those between here and Jackson. There's a really good example of it. I-94 cuts right through it over by the Grass Lake area. As part of the Waterloo Recreation Area, you can walk along it. There's some good examples of it. There's one over by, what's the Washtenaw County Park? Lake Linden, Park Linden?
Yeah, there's a really good one.
Yeah, there's one there.
So the esker is the ridge that forms?
Yeah, the esker is that sand and gravel ridge
Okay.
that forms underneath the ice, and so it looks like a snake in the topography, and this big ridge winding around through the woods, and when you dig into it, sand and gravel formed by flowing water,
Larry, I
building up.
always taught it right. There was a river in the ice, and the river deposits, like any river does, sediment, and then the ice melts. So instead of carving down a valley, it builds up a ridge, but is that too simple? I think it might be.
For the esker?
Yeah, for the esker, like it's just like the river valley never forms it. Like a river always deposits
So you're saying
material, but
in a valley on the ice,
yeah, it's
and then
a
the
valley.
ice melts, and then that sediment comes down?
Yeah, that's how, like I would
Yeah.
talk about it like the river that is that esker carves a valley in the ice, but then
Yeah.
the valley disappears because it's in the ice.
Yeah, and then you got a ridge left.
And then you have a ridge left. Is that
Yeah.
wrong to think
No,
about
no,
that?
it can be that way too.
Oh, it can be that way too.
It can be
Okay.
that way too.
Okay.
But a lot of times when it forms that way, it's up on the ice, and then after the ice melts, the deposits come down, and you can see
Uh-huh.
the deposits that, you can see things in I have, what, 10 minutes? Oh, gotta keep moving. So those deposits then get disturbed.
How did he see that?
But it's on my right side, not my left.
Tim's good.
So here's some examples of ice and sediment on top as the ice is melting and coming off into a lake down here. I gotta move fast, so the end moraine's there. Here's a rock that I found up in Canada, and I had to leave it there, I couldn't fit it in the paper. But then glaciers moved it,
Wow.
I couldn't. some rocks on top of the Defiance Moraine in Livonia. So, uh-oh, what did I touch?
Did too.
Okay. So there's a moraine that runs along here called the Defiance Moraine, and we'll look at that. And it's more like a lateral moraine. You get the Huron lobe, the Erie lobe, and you can kind of look at that as like one big lobe to some degree. And there's a suture between the Saginaw lobe, the ice that came through the Saginaw area over here, the Huron Erie area here, and then when those melted away, then you had this interlobate area in between, a lot of sand and gravel depositing, a lot of water flowing in between, and creating the sand and gravel in those areas. So I'm gonna move quick through here. And so you can see debris coming off into those low areas, and that extends from down by Grass Lake, going up into Oakland County, that area where there's a lot of sand and gravel, you know, the sand and gravel pits up by Oxford, that area, that's in that area in between these lobes. And some of these deposits that were created that we can walk on out by Grass Lake, head of outwash, the ice was here, a lot of sand and gravel depositing is more like a fan. So it wasn't a delta, it was on land, so it was like a big fan of sand and gravel. And that's what we have, this outwash plain in that area over by Grass Lake. And so we have, in this area, between these lobes, there are moraines that were created by the ice as it was melting away and moving forward, but then a lot of water coming off and depositing sand and gravel in between the moraines. And so it's a mix. And so when you think of, you know, how plants would grow in the different environments, a lot of different things in pretty close proximity. Sand and gravel, well-drained soils, moraines, a lot of clay, a different type of environment for plants and for wildlife. So more examples of that. And so it would look like this, a lot of water flowing off, a lot of sand and gravel, braided streams. Now the reason we had the Defiance Moraine form in here is because of a big sandstone ridge that stopped the ice. It doesn't take a whole lot for the glaciers to stall out and stop moving because of a little ridge in the bedrock below. And so as the glaciers were thinning down, they had less energy. It couldn't pop over that little bedrock ridge, so it stopped here, continued to flow, but then dumped material on top of the bedrock ridge that was there. So you have this big moraine, this end moraine, that comes down through here. And so we'll look at some examples of this. What do we have here? This is in Livonia, looking out toward Dearborn out there to the Glass House. Ford. So that's you know, standing on the ridge and looking out over these lake plain areas. So as the glaciers retreated, there were lakes, great big stages of Great Lakes out in front of the ice as the ice was melting away. And so we're looking over that lake plain area in that photo.
That's at Schoolcraft College, right?
Yeah, and as the lake levels dropped, they formed beach ridges in this flat area out here. And so the red lines are the beach ridges, you know, constructional beach ridges, and behind the ridges are some wetland areas. And some of those still, you know, are still there. Ridge Road over by Canton, that's running right on one of those ridges, Lake Whittlesea, an old Great Lakes shoreline. It was a constructional shoreline. They just built the road right on top of it. So if you go along it, you'll notice that. Going up Woodward Avenue and into up by Lone Pine Road or Long Lake Road. That's when the glaciers were forming the Defiance Moraine. The water coming off the glacier then ran down in between portions of the moraine, and this pink is sand and gravel, depositing sand and gravel in a valley down here, and that big dip of that valley that Woodward Avenue goes through over by Long Lake is that valley that was a lot of water. So there's a huge river running down here coming from ice. So there's ice sheet up over there, a huge river running down here carrying that sand and gravel out to the lake that was out in front of the glacier. This is looking at that valley from the other direction. And here's up by Stony Creek Metro Park looking south toward Detroit. On a good day you can see the skyline of Detroit from up there. And that's the lake plain area down below. and the moraine, standing on the moraine back to the north. So this is showing some of the advances and then retreats, some of the little sub-advances that occurred in the moraines that were left at various times. So it would look like this, a big ice sheet, upland areas and lakes in between. And the water had to go in various directions depending on when the ice was blocking routes and forcing movement in different directions. So sometimes the water flowed to the west over toward the Mississippi area. Other times it flowed around this ice over toward the Atlantic Sea.
About 5.
Okay, and you notice this is an interesting shot. This is the Defiance Moraine up by 29 Mile Road, and look at the little benches on here. So in this case, when you're on a hillside, the Great Lake created a bench. So that's wave cut bench, and it's still there. The 29 Mile Road just goes right over the bench. They didn't even carve through it. It's still there, and you can follow it in, through the neighborhood there. So that was a Great Lake stage. That was the Great Lake, Lake Maumee, off in that direction, to the east. So it's really neat stuff. This is the Lake Plain area, that was leveled by the water moving, and as I mentioned, as the water's moving in different directions, a lot of sand and gravel. Here's 12,000 years ago. This is what the ice sheet looked like, and the Great Lakes in front of it. 11,850 years ago. 11,500 years ago. So it's melting away, backing off in lobes, 11,000 years ago. And the ice depresses the continent, just like that dense rock. The ice has some weight, and actually was pushing the crust down a little bit. And so it caused erosion that is still visible. There's a big gorge up there that the Mackinac Bridge has to go over. If you go down there, it's really deep there because it was a gorge at this time that was carved through there as the water was running through that zone.
Can I ask something about this slide?
Now this is 4,000 years ago, and so this is closer to what we have now.
Can I ask something
Sure.
about the last few slides?
Yes.
In particular, I'm so glad you stopped on this one. I see arrows flowing toward St. Lawrence. I see arrows flowing toward the Illinois River. It seems like maybe the water in this area flowed toward the Mississippi and then flowed toward the Atlantic in 2 different times.
Yeah,
Did it
yeah.
go back and forth like that?
Yep. There were times when the ice sheet over here to the east was blocking the flow to the Atlantic Ocean, so it forced water this way. And that's how you have the Grand River, parts of the Grand River were carved as water flowed over the middle of Michigan, and things like Grand Ledge, the cliffs that are out by Grand Ledge on the other side of Lansing, where, big amounts of water are running through the carving those sandstone cliffs. The valley in there at that time. So yeah, it was moving in different directions depending on what was lower. The ice, when the ice was sitting in a certain area, it was depressing the crust, and the water would move in front of the ice, preferentially in that direction. Yeah, so let me just show a few examples here. Water flowing through the ice. Here's our little cave here we saw. Here's an example over by Michigan Avenue and I-275. Lodgement till lodged in, but you can see the big boulder of limestone that was carved out of picked up out of the Lake Huron Basin and moved here and jammed in with this clay, and it was really tight clay. But there's signs of water flowing, so there's sand and gravel mixed in there, which we have to pay attention to when it's underneath a landfill. So we look at those types of things. Here's another example, another landfill down southern part of Wayne County. And this is interesting. This is the clay that was pushed in underneath the weight of the ice, and it's pretty dense. And then, there's examples of water, so there still was water flowing underneath the ice and mixing in with that till that was pushed in there, so we see this little channels of sand and gravel in that till. But then above that, we see this mottled clay and with some little bits of layers within it. And that was debris that was dumped off as the glacier backed off, as the glacier was melting. Debris was coming forward and dumping into the lake. And so it was, you think of dump truckloads of this till material, clay and rocks, sediment and rocks of all different sizes, all mixed together, dumping in there. And so it was just dumping in, but in between, you had just the silt and clay settling out of suspension in there. So this shows that this was deposited loosely into the lake. And so it's kind of mottled and looks like this. And that's kind of soft if you dig into it. But then the clay below that was pushed in under the weight of the ice is much harder. And then capped on top of all that is sand. So that sand is a sandbar in the lake as the lake level was coming down. So I got time out, done? Okay. So there's some examples of those types of deposits. I wanted to show one here. Sorry, but just a touch over. Where is it? Oh, there it is. This is Jane Deadlin's basement for her addition. Raise your hand, Jane. So I lived next to Jane at one point. This was when they dug a hole for a basement. I had to jump in. Sorry. And so it shows that debris that came down and deposited, that came off the glacier and deposited in the water, and then above that the sandbar or lakeshore sand as the lake level dropped. It could be a beach that's on top of that. But what's interesting about it is also the debris that below was some the glacier had backed away, and sediment washed out into the lake, and you could see thin layers of sediment in there. And so there was forming thin layers of sediment in the lake bottom. But then the glacier came forward again, and on top of that is that loose material, like a dump truck load of material that's dumped into the water and dumped down on top of that. And those little loose those thin layers that were very parallel and nicely lined at the bottom of the lake suddenly became deformed because of the weight of that material dumped on top of it. So you can see the progression of what happened here by the changes in the sediment. These are just other examples of deposits in the lake that we're done. I can go on all day.